Let's talk today how you can DIY yourself a wireless synchronized multi-room audio speaker. I want to give a short warning in advance. I worked on this project in 2022, so this means this video here is made mainly out of archived material I had stored in my cloud. So please be aware that the software ecosystem this project builds around has probably advanced since then, and also some chips I used are end of lifetime meanwhile. Let's have a look on the project goal first. So my goal was to create a Sonos style multi-room audio with exactly one pair of stereo speakers. Everything should be fully wireless, and I wanted to have a tight audio playback synchronization so we have acceptable stereo playback in a paired configuration. I also want to have some sort of standalone mode so that I can connect directly, for example, a 3.5mm input jack. Everything should be controllable by an Android or by an iOS application. The actual onboarding configuration shall happen via an internal HTTP server, and I want to have at least support for Spotify Connect, AirPlay, web radio, and as mentioned above already, an analog audio input. Of course, I didn't want to start from scratch, so I checked already what other projects were available on the internet. So the most interesting project, which also became the base now of this one here, was Snapcast. It's basically an open source multi-room audio project. There are server and client implementations out there for Mac, Linux, and also Windows. You can use third-party apps for the audio input, and there are apps outside there you can use on iOS or Android to control everything. The next thing was that I found an open source implementation of a Spotify client. So this was also nice because it can be used in combination with Snapcast also. So this means you can stream Spotify also directly from your smartphone Spotify app via Spotify Connect. In that case, we also got an implementation of the Apple AirPlay protocol, which could be also used in combination here with Snapcast. So this means I was able to stream from my Mac or from my iPhone, for example, music directly. And the last thing was, of course, that there was sort of like a music player service also available. What I was able also to, for example, stream music from an MP3 or WAV files connected somewhere to my host, or also use, for example, web radio. And yeah, those three ones were directly able being used together here with Snapcast, which is really an awesome multi-room audio open source project. Now let's have a look how I were setting up my system. So I used a Raspberry Pi 4 here, which is my central audio server. Here you can see there was a Snapcast server running on it. And I also installed the other project which I was showing you beforehand. So for example, the Spotify Connect, the Apple AirPlay streaming service, so that I was able here to stream from web radio. And it is also possible that I were able to connect, for example, USB audio grabber and directly stream music, for example, from analog audio input source to the Snapcast server, and with that distribute everything to other speakers. So the most convenient way to use Snapcast would be just to use, for example, another Raspberry Pi, install the Snapcast client on here and connect some speakers. But what I was actually targeting was to make my own custom Snapcast loudspeaker, in that case with an own hardware software implementation. So my basis for this project was, once again, probably you have seen that speaker already in some of my previous video, that small Canton Plus GX3 speaker. So what I did was I took a pair of them and I teared it down. And then I was able to have a look inside, how everything looks inside mechanically. Of course, there was a passive X over, which I targeted to replace also later on with an internal DSP. But let's have a look now on my PCB circuit concept. The idea was basically pretty simple. So I just wanted to create a small PCB which was able to fit inside this small speaker here. And I came up with following. Let's say I have a central 15 volts input supply here. I have some DC-DC regulator and some post LDOs to create the digital supplies for 3.3 volts and the 1.8 volts. And then I also used an MA2304 DNS Class D multi-level Class D amplifier with an integrated DSP chipset. And the heart of this PCB should be a PSOC62 microcontroller attached with a CIW4343 Wi-Fi chipset. And this was the basis to run a custom Snapcast client. In order to also have the auxiliary analog audio input, I attached an additional PCM1808 ADC in that case. Of course, there were some other things attached, for example, a capsense field slider for volume control later on, some analog switch you can see here, and of course an additional LED here for showing or indicating the status of the device. This is now how my PCB looked like, which was able to fit mechanically inside into the Canton speaker. What was in there, as already shown in the block diagram before, I had here a small Cypress SOM, so it was basically a system on a module together with the PSOC62 microcontroller and also the Wi-Fi chipset attached. This was soldered directly here on the board. Here in the middle you can see the multi-level Class D amp with the integrated DSP chipset. I had here my speaker connectors. Here on the right side there was my power connector. I also had here the ADC stereo audio input directly with the ADC next to it. And here were the connectors for the status LED and the user button. On the back side there was the capsense slider integrated because that was basically facing to the top of the speaker. So the idea was basically that you can just swipe with your finger over the speaker, which is basically sensed by this capsense slider here inside so that you can control the volume later on. So originally, the speaker was targeted to have a single amplifier channel. And then you have this passive X-over inside, which makes the frequency split between the tweeter and the woofer. And the idea was to emulate this inside the DSP. The good point was now that the MA2304 DNS amplifier chip, what we have here in use, has an integrated signal processor. So the idea is basically, let's try to emulate it with the software-based equivalent of this passive X-over and use two separate amplifier channels for the tweeter and the woofer later on. What I was doing then, so I'm not sure if it was the best approach, but it somehow worked, that I tried to find out the values of this passive X-over for the capacitors, inductors, and I also measured the DC resistance of the tweeter and the woofer and just tried to simulate its AC behavior in SPICE. So I was able to find out, for example, okay, it was both a second order high pass low pass filter, and I was able to, for example, find out where the -6 dB point of the high pass filter, but also where the crossing point of the low pass filter was. Based on those values I was able to find out, I was using now this Merus Audio DSP configuration tool and put those values into that. Additional to the pure crossover, I also put an additional 45 Hz low cut in this case, so that we have no super low frequencies going into the woofer. I also did an additional gain reduction on the tweeter because it was a little bit too loud in advance, and of course I also used the internal limiter so that I was not able to overdrive the speakers both. And on top of that I also did some minor EQs just for my personal preference that it sounded a little bit better, but I did not do any additional measurements of the speaker or something like that. And then it was time to reassemble the speaker. So as you can see here, I was directly soldering some JST cables to the woofer and also to the tweeter. And you see that I also integrated here. It was a very quick and dirty solution, but you see here that the LED into the tweeter was also integrated for the status indication. Then I put some holes on the backside of the speaker, mainly for the power input, but also for the analog audio input and also for the firmware update port, which I also was running over 3.5mm port, and then also a switch, which you will see later on for what the purpose of that was. Then I also put the damping wool again inside the speaker. And then it was time to assemble the PCB inside. And now you can see how the PCB was fitting inside the speaker and why I had the capsense slider on the back of that PCB so that I was able to control the volume from the top side of the speaker. Before reassembling everything, I tried or made, of course, an additional test if everything was working fine. And then I had my finished speaker. Here you can see another picture of the backside. As I said once again, I'm not very good in mechanical things, and this really looks a little bit quick and dirty, but it worked. So here in the middle, there's the power input. I have 2 ports for the analog audio input and also the UART debug firmware upgrade port, and I have the user button. So this user button was mainly targeted either, depending on how long you press it during startup, that you were either able to go into the Wi-Fi configuration mode, or if you are pressing it longer, that it jumps into the bootloader and is doing the firmware upgrade mechanism. Okay, now let's have a look how the Snapcast protocol itself is working. So in general, the client has to actively open a connections towards the server and start with a so-called hello message. So this hello message includes, for example, information like what architecture is it running on, what is the client name, for example, bedroom left speaker. It has some sort of host name. There are some IDs, instances, MAC addresses, what operating system it is running on. And after that, the server is returning with a so-called server settings message. Once there is an information how long the buffer should be in terms of milliseconds, how long the latency should be, if the speaker should be muted or not, and what the volume actually is. After that message, directly the Snapcast server sends an additional codec information message. So it tells you, for example, which sample rate it is, which audio format. In this case, it's just a standard wave format, which means we are getting our raw samples with 2 channels and a 16-bit little Endian audio format. And then basically the rest of the communication starts. So this means we will have regular time sync messages going back and forth between the server and the client to realize its time synchronization together. And in between those time synchronization messages, there will be the audio chunks transmitted. So typically you will have audio chunks of 20 milliseconds, but if I remember correctly, this was configurable. And of course, an audio recording timestamp, so that we were calculating back together with the buffer milliseconds value here, when this piece of audio actually should be played back exactly. Here is once again a detailed overview how time synchronization mechanism is working. I don't want to go into detail now, so you can look it up later on yourself how exactly it is working. But the general idea is the client is sending a message to the server, which includes an information when basically this message was sent based on the time the client had. And afterwards, the server can basically make a timestamp when this message was received. And it directly sends back also a message back to the client, for example, with the information when, in terms of server time, this message was received and what the actual send time of the server was. And the main assumption what behind this is that we assume that the network delay in both directions, so from client to server and from server back to client, is symmetric, because this is something we actually don't know how long the delay time really is in the end. But using this formula then later on, you will see that basically the actually network delay time in the formula will subtract itself, so it doesn't matter in the end anymore. And with this, we are able to precisely calculate back what our own offset is in relation to the time to the server. And with this, it is possible to exactly calculate back the server's time, which is then later on used for the time accurate playback of the audio samples. Let's have a quick look in the software implementation, which was running on the PSOC62 device. So as you can see here on the left side, we have our Wi-Fi chip, which was just connected via a 4-bit SDIO interface to the microcontroller. Then there was, of course, like a proprietary driver for this Wi-Fi chipset. We have an SDIO host driver, and we used the LWIP protocol stack, which enabled us TCP style communication to the server. Everything then here on the right side, like this greenish color, this was basically then self-implemented. So this means we have here a protocol engine which can talk the Snapcast protocol I presented to you. And then you see there are 2 paths ongoing. So on the one hand side, we are getting here our audio chunks with the playback timestamps, which is directly fed into some sort of thread safe time aware audio FIFO. And on the other one hand side, there was this time synchronization ongoing. Not exactly time synchronization, so it's just a value which gives an indication of what exactly the time difference between the local client and the server is. And unfortunately, Wi-Fi is very, very jittery, especially with this low cost 1x1 2.4 gigahertz Wi-Fi chip. So what I did was we are feeding those time diff values in some sort of ring buffer, which is continuously updated. And this is basically sorted. And we will get here like a minimum to maximum value, which means the lower the value is, meaning that most probably the server to client time was higher than in reality. And on the other one hand side, we get here our maximum values, which means the client to server times were probably too high. But the values here in the middle is the most trustworthy zone, basically, which means that those values mentioned here are probably exactly those values where we can assume that the delay times between client to server and server to client were the most accurate ones, which we used then further for our audio resynchronization mechanism here. In general, the audio synchronization mechanism was working this way. We had here our I2S peripheral, which was running in a static 44.1 kilohertz sample rate. And then we got our DMA. So the DMA operated in block sizes of 512 samples, but every time this DMA interrupt was firing an interrupt, it was basically making a time snapshot. And together with our best guess server offset, we were basically able to recalculate when this interrupt from this audio DMA was firing in terms of server time. And together with our, let's say, time-aware audio FIFO, which means we have a precise timestamp for every audio sample, we were basically recalculating how much or like how accurate we are synchronizing currently our audio playback. And here we have like our audio playback mechanism, so which gets on the one hand side the audio data, but on the other one hand side also what we call the playback time difference. And with that, we are calculating or like synchronizing the audio stream because we know if the audio playback is too much in the future or basically too late in the past. And with this, it was basically a resampled, retiming kind of mechanism going on here, which was then feeding the audio samples in the audio buffer, which were basically played out over this I2S peripheral into our amplifier at the end of the day. As I said, the DMA was capable of making a time snapshot every time there was a buffer switch over between the two ping pong audio DMA buffers. And on the other one hand side, we had an audio FIFO, which had an internal time snapshot. So we were able to have a dedicated timestamp for every audio sample. And as soon as the audio DMA is starting and the Snapcast client is receiving the data, which means that the topmost sample in our audio FIFO is getting older and older in time, which is meaning that basically the FIFO data is moving forward in time. But we have here our reference time and we have what I was called an open window, which means we are using reference time with some plus minus offset value in time. And as soon as the first sample of the FIFO or the topmost sample of the FIFO is fitting some sort in this time window, then basically the playback starts fetching samples from the FIFO and moving it into the DMA slots from the I2S DMA. And once this has started, which means we have sort of a plus minus accurate synchronization, but it was not really precisely synchronized. So therefore, I had two levels of synchronization. So this means it was once a hard synchronization and once a fine granular synchronization. What happens here is basically we have here our DMA reference time and also we have always the topmost time of the FIFO. And every time there is like a DMA switch over, we can basically check the reference time of the DMA, basically the server's reference time against our top time of the internal FIFO, and we are able to calculate the so-called playback offset. And in case we are playing too early, which would means actually we need to slow down the stream a little bit, which virtually means that we need to insert some additional samples. And this is done not by just like throwing away samples or like copying samples, but there was a small upsample process in this case ongoing. So this means instead of 512 samples, which was the regular DMA buffer size, we only fetched, for example, 511 samples and upsampled this once again to 512 to play back this in the next DMA slot. And of course, this diagram here is only showing the general concept idea behind. So in general, or in reality, this operation was a bit more advanced and operates smoothly over like longer time frames. But with this idea, actually, we were able then to minimize the playback offset. What I want to make clear is that actually something like this is implemented by fine adjusting an audio PLL. But as I was using the PLL of the PSOC62, which was internally in there, unfortunately the fine granularity adjustment of what the PLL allowed was insufficient for proper resynchronization of the stream. So the idea was, okay, we keep basically a stable sample rate. We don't touch the PLL anymore, so it runs statically, but instead we are using adaptive sample rate conversion. But if we are thinking about it, then adaptive sample rate conversion at the end of the day is just a software-based DSP counterpart, let's say, of adjusting hardware-based PLL, right? And this was, once again, the fine synchronization, but the opposite way around, in case we are basically did our playback too late. In this case, instead of fetching 512 samples, we fetched one sample more. We downsampled this to 512, and this way we were also able to minimize our playback offset in this case to keep the synchronization. Now let's have a look how this implementation behaved against a real-world product you can buy. So as a reference, I had the Sonos IKEA Symfonisk system, and I was playing pulsed sine wave signals, which I was able to record with two microphones in that case. Here you can see in Audacity basically the deviation. So the deviation was a little bit moving in its value over time, but the best thing I was able to measure was around 320 microseconds in that case. The same test I also did with my PCB implementation. So as you can see, this was in a pretty early stage, so the PCB boards were not in the speakers yet. Instead, it was just like in a passive way connected to the speakers, but it gave me a good indication of the synchronization, and I just redid the same test here. And together with my implementation, I was able to reach roughly 660 microseconds deviation. Of course, it was not that great as the original Sonos speakers, but it was fairly good enough to listen like in a stereo setup if you were a couple of meters away from the speakers. But of course, it was really just a proof of concept and quick and dirty implementation. So I guess there's a lot of other ideas and potentially advancements and improvements you can do in there. So now let's have a look what other Snapcast system operations I was targeting to implement. So this is the standard Snapcast system I was using. So you have somewhere in your home your central Wi-Fi router, Wi-Fi access point. And in my case, I had the Raspberry Pi just connected via an Ethernet cable directly to my router. And my two speakers were basically just acting as a Wi-Fi client and as a Snapcast client against the Raspberry Pi in here. And I was using my phone to control everything. Another idea I had, as I was showing to you, was the direct auxiliary input operation. So in this case, you just connect your smartphone directly to the speaker via an aux cable, and then you can just listen to music. And then I had another idea. Why not spin this idea further and make one of the speakers a Snapcast server itself? So what I was implementing was that one of the speaker acted itself as a Wi-Fi access point and a Snapcast server, while the other speaker was basically keeping a Wi-Fi client, Snapcast client. So the point was I had it sort of experimentally working, but it is still in a very unreliable working condition. So I was facing, unfortunately, a lot of heavy jittering, bandwidth issues and like audio dropouts. So just to make you aware, in the GitHub project I was uploading, this code is still in there if you want to play around with it, but it was not really functional. But I also did not invest further time into debugging this at the end of the day. But the idea in general, it was working sort of a bit, but I did not have any further time to continue working on this. So, but now let's have a quick look on how the Wi-Fi onboarding process looks like. So as you were able to see, there was a small button at the back of the speaker. You can press it down and then the speaker acts basically as a Wi-Fi hotspot. And then you see there is a Wi-Fi network which is called Snapcast Client. You can directly connect into it, and then it was showing a web page. So you were able, for example, to control the brightness of the front LED. You were able to select the operation mode, if it just be like direct aux in operation, if it should be in server mode itself, or if it just act like as a Wi-Fi client itself. Configure the IP address of the Snapcast server. Then you were able to put in your Wi-Fi credentials and of course the audio settings. So for example, you can say you are the left, or you only want to play out the left channel of the left-right signal stream from the server, or only the right channel. You were able to apply some basic equalizing bass and treble, and of course to choose the DSP setup. In this case, it was like a dedicated DSP setup for the Canton speaker as a two-way X over with a 45 Hz low cut input. Yeah, and as soon pressing the save button, it will give you a message which says data was saved. You can restart the device. And I also implemented some data integrity or data validity check. So for example, if you are making some signs which are not allowed here or some characters, it will show you like a warning message that this was not fine. So let's make a short demonstration of how the system is working. You can see now the two LEDs are lighting up constant. So this means it is connected to the Wi-Fi and also connected to the server and is ready to play. I can also show you what happens if I plug out here one power supply. It seems there's a big capacitor. Okay, it was the left one. Then I reconnect it. And you see now it's pulse blinking. So this means it is actually connecting now to the server. This takes which were a couple of seconds, probably also a minute, not so long. So okay, now we are connected to the server. It has stable Wi-Fi connection connecting to the server, but it actually takes like another minute until the time synchronization is correct. So now I can open here my smartphone. And I have already here this Snapcast control app, and you can see here, this is basically now my right speaker. I can like change the volume, my left speaker change the volume, or here even my smartphone, so I can theoretically press the play button and the smartphone would also synchronously play the audio from the sound system, but I have disabled this now. But what is also possible is that I can change the volume of the whole system together here. So not sure why the left speaker is a little bit behind, but now it seems to work okay-ish. So now we have here the stream Spotify. You see this idle because we are not playing anything at the moment. We can rename this room here and say, okay, we are call it room. And we say, okay, here we have to stream Spotify. I can also choose AirPlay or MPD, which is basically the web radio player. But let's stay to Spotify for the moment. Okay, now let's switch to the Spotify app. You can see already here Snapcast is already enabled. So I can press theoretically this iPhone. Then it would play here from my smartphone directly. Or I select here Snapcast. And then it will start playing here over my two speakers. So here the sound was synchronous between the two speakers. Now I can also change here, for example, to the stream of AirPlay. Okay, now select back. So now, of course, AirPlay is not playing anything, so we are don't hearing any sound. It also states it is idle. So we go here, for example, to Mixcloud. We are playing here something. But this is now locally from my smartphone, of course. I press here, choose Snapcast. bit. Now let's show the last one. This is the MPD player. Now I have to go into my MPD app, that one here. So we can choose here, for example, not sure, Latio Charivari. Select back.
Also, Ihre Reifen, die sind so richtig am Ende, da braucht's was Neues.
Oh, stimmt. Schatz, gute Neu...
Oh, life is beautiful. You were the light for me to find my truth. I just wanna say thank you. Leaving to find love.
Of course, I can also say now, I want to play my smartphone, for example. Then I should be able to hear it locally. Okay, I can't hear it because it's restreaming to AirPlay now. But now it's working. But you hear the speaker is synchronous also to the smartphone. Yeah, that was the demo. And this is now once again demonstration of the direct auxiliary input mode. This means Wi-Fi is actually completely disabled. It is really just working for its own. And as you can see, I have here the lower port, which is like a standard aux cable. So the upper port is for the firmware update. Yeah, and I have connected now here via cable and that lightning adapter now my smartphone. I can play here just music. Yeah, and it's super low latency, so you can really just connect it to your computer. There is like around about 10 milliseconds of processing delay, but that's really not much. So this is now a small presentation of the setup mode. I have connected here the speaker, and as I plugged in here the power supply, I was pressing this button here for 3 seconds. So it now switched to the configuration mode. You can see that also here with the fast switching LED. And as you can see, I have here already the Snapcast client Wi-Fi instance. I can connect now to the speaker. So it takes a moment, now it is connected. Now I can switch over here to Chrome, enter this IP address here, the 192.168.10 and 1, which is actually the IP address now of that speaker. So iPad automatically gets a DHCP address from the speaker, and then you can see already here the configuration which was inside. So okay, you say we want to keep here 25% brightness, like for the mode. I have here direct aux in mode or the Wi-Fi client snap client mode. This is now the right speaker, this is correct, but what I have to change now is the Snapcast server address, because this has now changed, which is actually the 78.26 in my case. Alright, here I have my Wi-Fi SSID from my home network. And I also want here, of course, that this is the right speaker. Okay, this is the equalizing, and this is of course the DSP setup for the integrated Meros amplifier, which I leave it like that. Then I press save here and it says, okay, data was saved, you can restart the device.